Okay, thank you. Thanks everyone for being here. So, I'll talk about transfer learning. First, I'll explain what transfer learning is about, and the talk is based on joint work with Guillaume Martinet and some ongoing work with Steve Haneke. So what is transfer? What is transfer learning? Transfer learning, the most basic way to explain it is we have data from a particular distribution, and we train on that particular data from that distribution. However, we are interested in performance under a different distribution than the distribution on which we trained. So that's the basic premise. And so that's what I have here. We train on some distribution P, but we are interested in doing well under a distribution Q. So I'll start with some quick motivation. So here's the motivation, Siri on your phone or any such speech recognition system. So Siri, back when it came out, was trained mostly on data collected from American English speakers, on American English. And when I tried it, and when a lot of people with my type of accent tried it, it didn't work, right? It didn't work. Why? Because the data was collected on a particular population, but we were interested in making it work on a much more general population, right? And so that's sort of the issue. And what did Apple do? They went back and tried to collect a lot more data. And this is an expensive process. They had to collect a lot more data over many years and retrain their software. So the problem of transfer learning in machine learning is how can we speed up such process, right? Here is one basic question I'm sort of interested in is how much new data should they collect? They want to reduce their cost in collecting more representative data, and how little of it do they need to collect in order to transfer properly? So that's the first question. Another high-level question is what are the optimal approaches once they've collected this data? What are the optimal approaches to properly transfer information from what they had trained before to the new setting? I hope that is clear. Those two questions, both those questions are about minimizing the cost of transfer. So transfer is a fairly general problem. You have transfer problems in medicine, in genomics, in smart cities, in a lot of the emerging applications where the data that you collect is not very representative of the eventual population that you're targeting, right? So I'll have this notion of a source data that you've collected, and P will represent that source data. So you train a classifier on P, that source data, and then you're trying to transfer to a target distribution. So we'll view the source data as being collected from a probability distribution, and then the target being another probability distribution, okay? So again, the question we sort of is going to drive the talk is how much new data should be collected, right? Underlying that question is, here is a first basic question, which is there enough information in P about the target Q? And what do we even mean by information here, right? The next question is, if there is not enough information, how much data then should we collect, and how should that depend on the amount of information between P and Q? Would unlabeled target data suffice? And what we mean by unlabeled target here, would unlabeled target data suffice? Why we care about this question is because in machine learning, often unlabeled data is much cheaper than labeled data. So a lot of people have been trying to solve the question of transfer by collecting unlabeled data. So the mathematical question being asked here is, would unlabeled data help, right? So I hope this motivation is somewhat clear. And underlying all these questions, you can imagine that, okay, we need to sort of understand what we mean by information between P and Q. And very colloquially, I'll call that the distance between P and Q. What do we mean by how far is P from Q, right? And that will depend on the problem we're trying to solve, but the problem will sort of fix attention to will be the problem of classification here, all right? Now, again, I say that transfer is a very general problem, and in fact, there are tons of heuristics out there to attack the problem of transfer. There are many heuristics out there. However, theoreticians have only started looking at it maybe about 7-10 years ago, and we still don't have basic answers to these questions, to these very basic questions. Okay? So we'll try to start giving some answers to these questions. All right. First thing is the notion of distance. What notion of distance do we want between P and Q? What notion of distance captures the limit, the performance limit of transfer? So such notion of distance remains unclear. People have tried various notions, and I'll first start by giving you a sense of the notions of distance between distributions that have been tried over the last 10 years by theoreticians. Okay, so here is a basic intuition. Transfer, that should drive a notion of distance. Transfer is easiest if the source distribution P has sufficient mass in regions that we care about under the target Q. Okay, so here is a simple cartoon. In this cartoon, we have a distribution on squares and triangles. Imagine these being all types of accents, and these being accents sort of mine, right? Or Scottish accents, or accents that are hard for Siri. And then we have this distribution, and we sample data from it, and we want to transfer to this other distribution, right? So how hard transfer would be will have to do with how much the source covers these areas on the P. Right? I hope that intuition is somewhat clear. And so a lot of the notions of distance between distributions that have been tried sort of try to encode that basic intuition. So here are some examples of notions. So extensions of total variation, some common notions. So total variation being just looking at the soup of the difference of masses assigned to any measurable set over the space. And extensions of it that have been tried just limit attention to particular measurable sets over the space. Okay? Those are sort of the some of the most natural things people have tried, because total variation is one of those notions that is readily available in probability. Other notions Other notions that have been tried have to do with density ratios. So I'm looking at the ratio of densities between P and Q, right? And particular norms of these density ratios have also been attempted. And notions that are related to density ratios, such as KL divergence and such things, right, have all been tried. So the first question we're asking here is whether any of these notions, any of these typical notions of distance between distributions or divergence between distributions capture the essence of transfer. Do they tell us when transfer is hard or easy, right? And in order to answer all the questions that I laid out at first, like how much data should we collect, how far are things, we need to understand whether any of these notions is the right notion to capture the performance limit of transfer. Okay? So please stop me anytime. So here are some of the main results that people have had, that theoreticians have had about these notions. So here I'm putting down all the type of notions that people can imagine. And in fact, if you look at the vast literature on transfer, people have used all these type of notions, any notion of, any existing notion of divergence or distance between distributions. And the type of result they have is the following, is that the closer P is to Q, the easier transfer is. Right? So that's one direction. If P is close to Q, transfer is easy. So that's to be expected. It's sort of a sanity check. However, the question we sort of want to answer is, under any of these notions, do we have the reverse? If P is far from Q, does that mean that transfer is hard? If we don't have the reverse, then somehow these notions do not capture the performance limits of transfer. And I hope that is clear. We want sort of an if and only if statement. Transfer is easy when P and Q are close under this notion. Transfer is hard if P and Q are far under these notions, and that's the sort of notion we're trying to arrive at. Okay. So here is some simple some simple, again, cartoon to illustrate what you can get under these type of notions, right? So my claim is that under much of these notions, much of these notions can be a little over pessimistic. They might, P and Q might appear to be far under these notions. However, transfer remains easy. So here is a simple example to start with. Again, the same cartoon, but now under this cartoon, we can set total variation and extensions of total variation such as DA divergence, Y discrepancy. These are the main extensions in the theoretical literature. We can set these extensions close to 1/2. Close to 1/2 for classification will mean that the best rate you can get on the classification is 1/2, which means that you cannot classify, right? And so we can easily make these notions very large in classification. Just look at this set here and this set here. The difference in the mass of this set can be pulled as far as possible. However, there is an easy transfer here, because imagine that I put a linear classifier here. It will transfer easily to this place. It could be even other algorithms. I could do nearest neighbors here. It will transfer easily to this case. So under those type of notions, the distributions might appear far, but classification is easy to transfer. Okay, so I hope that point is clear. Here is another example. The source distribution is this, the target is this, and the target lies on the submanifold of the space. Okay? If I use notions such as density ratios, the density ratio will blow up to infinity. If I use KL divergence, Rényi divergence, all those things will blow up to infinity. However, this is again a case where I can put a line and the line will classify. Well, so transfer again is easy in these cases. So even though if I use these type of notions, the two distributions appear infinitely far apart. I hope that point is clear. So we need a notion that can capture this, the fact that these things are easy to transfer. Okay. So any question up till here? All right. So I'll just jump to the type of notions that we are proposing in this line of work. So first, we'll set up the whole problem formally. And the formal setup is the following. So I first assume, I first simplify the setting. So we are in a classification setting. I want to predict a label Y in terms of covariate X. And, but I'm going to assume so-called covariate shift. This is the most common assumption in theoretical literature on transfer. It's assuming that P of Y given X is equal to Q of Y given X, but the distribution QX and the distribution PX are different from each other. So in other words, the labeling, the conditional labeling distribution is the same, but the masses are different, okay? And this is well justified by a lot of applications of transfer. So if you're thinking of computer vision, an image, the likelihood of a label or an object in an image does not usually change if I change the database. Okay. So I'm given source data. So this is the key assumption that we're going to make, which is fairly different from the way people have set up the problem before. I'm going to assume that I have labeled data from the source, NP label data from the source, and NQ label data from the target. Why do I assume label data from the target? Because often, for two reasons, often in the practice of transfer, people would get some labels, right? But the most important reason why we are assuming this is because we want to understand the value of acquiring more labels. So we assume in our setup that our classifier has access to label sample from the source, label sample from the target, and can do can apply any procedure to return a good classifier. And we want to understand for such a classifier that has access to both samples under different sample sizes, what is the performance limits they can attain. I hope that is clear. All right, so this is all I said. The target error is some integral under Q, the target distribution of our classification loss. Okay. So here the basic information theoretic equation is what are the limits, which error Q, which is in fact a risk, which risk is achievable in terms of both sample sizes. So we want to understand the minimax rate here in terms of not just one sample size, but in terms of both sample sizes. Here I have to say that a lot of the theoretical work so far had only assumed one sample. And the other sample was, NQ was assumed to be 0. And because of that, they could not capture the apport of sampling more target distribution, okay? So now, which notion of distance between PQ captures this error, captures the limit of this error? So here is the notion that we're going to propose. However, so here's the notion. It was in a work that appeared, I called 2018. And so the main intuition, remember, is that we want P to assign enough mass to regions of significant Q mass. That's the intuition, and we'll try to capture that intuition again, okay? And so we propose this notion that we call the transfer exponent. And I'll describe it in a second what the transfer exponent is. But imagine that BXR is a ball in my space centered at X of radius R, right? So the notion is this notion is just saying that the mass assigned by P to a particle, to such a ball, is R to the gamma greater times greater than the mass assigned by Q to the ball. Okay, so gamma is parameterizing how much relative mass are assigned by the two distributions. Okay, and we'll show that this simple gamma actually captures the performance limit if in an if and only if statement. So here is a simple illustration. Again, I look at balls. I look at the mass assigned by Q. I look at the mass assigned by P. And I factor in the size of the ball. That's another important part. I factor in the size of the ball. And I look at all possible balls, R going down to 0, X going through the entire space. And this will capture a continuum of easy to hard transfer, as we will show. Okay? Large gamma, very hard transfer, is low gamma, very easy transfer. So first, let's try to understand what this gamma means. Let's look at the extremes, gamma equal to infinity and gamma equal to 0. At gamma equal to infinity, this is what we have. It just captures our intuition. Bad coverage. So bad coverage means here, P, the support of P is inside the support of Q. So there is a lot of the support of Q that is not covered by the support of P. In this case, gamma can be shown to be infinity. Okay. Good coverage is this, where P fully covers the support of Q. In this type of cases, typically gamma will be 0. So transfer will be very easy in these type of cases. Okay. Here, a quick thing that I'd like you to notice is that transfer happens to be an asymmetric. The distance in transfer happens to be asymmetric. This distance happens to be asymmetric. And transfer inherently is asymmetric, right? If I look at this, this here, I can transfer information from P to Q, but I cannot transfer information from Q to P. So what does that tell us? That tells us right away that metrics, notions of distance between distributions that are metrics, cannot capture transfer. I hope that is clear. People have tried, for instance, Wasserstein distance, because Wasserstein is the new cool thing in machine learning, but it will not capture transfer because it's very symmetric. This is what? Yeah.
So does it mean in particular that unless Q is absolutely continuous with respect to P, this thing will always be infinite? Like gamma will always be infinite?
If what?
If P is not absolutely continuous.
No, that's the key point. I don't need absolute continuity. I'll show you in an example in a second.
Isn't it kind of a Minkowski dimension of one versus the other?
It's actually, that's a very nice point. You can view it as some sort of, in fact, it's some sort of Rayleigh dimension. In the limit, it's some sort of relative Rayleigh dimension from one distribution to the other. Yeah, so that's a very good point. Okay, and that because of that also, we're not requiring absolute continuity. So here is now let's talk about the continuum, and those examples in the continuum of gamma from 0 to infinity would explain it better. So this is a simple case, sort of the type of image that one would show to explain Wasserstein distance. So Q is here. This is FQ, which is the density of Q. This is FQ, and P shift mass away from P and from Q. And how much mass is shifted away is captured by gamma. So gamma here is capturing how much mass is shifted away. Okay. Here is another example. This one shows. So this one shows that gamma, in some sense, is a measure of how close to singular P is Q is with respect to P. Okay. So in this example, Q is sort of uniform here. And P has a density that is going down to 0, and the rate at which it's going down to 0 is captured by gamma. Okay? And in that sense, this is very similar to what Rayleigh dimension will be capturing. This is another case where P has this support, and Q has a support that is lower dimensional than the support of P. In this case, you can show that gamma happens to be, if for instance the distributions were sort of uniform on each support, then you can show that gamma happens to be the difference in dimension. Okay. All right. So gamma is much more optimistic than the previous notions. So back to these examples here. In this example, where I could make total variation and extensions thereof close to 1/2, gamma will remain typically 0. Okay. In this other dimension, in this other example, gamma is exactly 1, and remains very small in this other example. Okay. All right. So gamma captures the performance limit. I haven't shown any theoretical result yet as to how. And so it's hard to describe the theoretical result, so I'll try to give you a sense of the type of result that we have obtained in terms of minimax rates, information theoretic minimax rates. So first, one has to understand one thing. It turns out that gamma is not enough to capture the performance limit of transfer. The performance limit of transfer is not just only about the distance from the two distributions, it's also about how hard the classification problem was. Okay? And that's a very nuanced point, but I can get back to it later. And so first, just to give you a sense of what we mean by how hard classification is, so here I'm showing two possible targets. Okay? You can imagine that classification under this target is very easy, and classification under this target is much harder. Right? I'm trying to classify blues away from squares away from triangles. Classification here is much harder. And so this is fairly well understood in classification, but the point here being made is that you can actually parameterize how hard classification is under the target. And the way you parameterize it has to do with the amount of noise in, around the decision boundary. And by noise, we mean how much overlap there is between the classes. Okay? So the amount of noise there is in the decision boundary is one way. And then the other important thing is how much mass Q is putting around the decision boundary. The reason why how much mass Q is putting around the decision boundary is that we are in a statistical framework where we're only observing Q through a finite sample. So if we're observing it through a finite sample, it has to be that it puts enough mass around the right decision boundary so that we can observe the decision boundary. So all this is just signal to noise ratio type thing in the end. Okay, so we parameterize this and we get a lot of different regimes of how hard classification is on top of gamma. All right, so performance limits. Now let me tell you the type of result we obtain. So again, just to remind you of the setup, we have NP data from the source, NQ data from the target. Okay. Any classifier has access to both labeled data, and we want to understand the minimax rates in terms of NQ and NP. So the theorem it's actually a series of theorems, but the overall result says this, that under a continuum of easy to hard regimes of classification, so we parameterize the whole continuum of easy to hard regimes of classification. Under a continuum of easy to hard regimes in classification, the minimax rate, so the best any algorithm can do, right? The best any algorithm can do is captured by a particular rate that is in terms of both sample sizes and in terms of gamma. So the key point here being that gamma is capturing this entire minimax rate under all these regimes of easy to hard classification. So the rates themselves are not so simple to describe within the little time I have, but I'll give you some examples of the rate. So here, under very hard classification, the rate takes this form. And by hard classification, I mean all we know, for instance, is that the decision boundary can be any nonlinear decision boundary. There is so much noise and such, right? So the rates then are non-parametric and depend exponentially on the dimension of the target space. This is the D. And how it depends on the dimension of the target space is given by a contribution from the source data, a contribution from the data from P, and a contribution from the target data. Here, what's interesting is that the contribution from the source data can be viewed as an effective sample size contributed by the source. And that effective sample size contributed by the source is given by gamma. Okay? And this is true in all the regimes that we considered. So here is an easy regime. Easy classification. Easy classification, we get back into into parametric rate, 1/2. And again, contribution from Q, and contribution from the source, characterized by gamma. Okay? And these are minimax rates. What, again, let me put it in other terms. What we mean by minimax rate is that there exists an algorithm that can attain this rate, always, but no algorithm can attain a rate faster than this. There is always a distribution under which no algorithm can attain a rate faster than this. I hope that is somewhat clear. So we get the if and only if statement. So the immediate message is that transfer is harder as gamma goes to infinity. If you look here, gamma goes to infinity. The contribution by the source, the effective source data size is 0. Okay? And as gamma goes close to 0, the source contributes more to the information under P. Another interesting result we get from just this characterization is that classification or transfer can be easy even when gamma is large. What that means is that even when the two distributions are far from each other, transfer can be easy. Why? Transfer can be easy exactly in those cases where classification under the target was easy.
Small question.
Mm-hmm.
Could the gamma be 0 when P is not equal to Q?
Yeah. Because of the they just have constant. Yeah, exactly. Okay. So here is a few other interesting messages that I'll go through somewhat quickly. But please stop me. I don't have to finish the talk. I'd rather I'd rather be clear. So benefits of unlabeled target data. We talked about that earlier. This is a question that is very important to practitioners. Can I use unlabeled data to help? Right, and so the rate, let me say something quickly about the rates actually. The rate I established, the lower bound I established using some extensions of Fano's inequality from information theory. And within establishing the rate, we allow the classifier to know the entire covariate distribution, both Px and Qx. What that means is that even if the classifier knows Px, so essentially knows Px and Qx, so essentially can sample infinite number of unlabeled data, the rate does not change. Okay, the limit does not change. So what that means is that there is always a distributions under which your unlabeled target data does not help at all in transfer, which was quite interesting to us because people expect that it should always help it, to some extent. The benefit of labeled target data, so we now understand that it's the most beneficial as this gamma goes to infinity. As gamma goes to infinity, you should sample more. And how much more you should sample is given sharply by this rate. The rate tells you exactly the relative contribution of P and the relative contribution of Q, and tells you so at what point there is enough data from the target to change the rate. Okay. So here is a more practical question. Can we automate target sampling? Okay, so why? Because even though I know the sharp transition at which sampling from the target helps me, the transition depends on gamma, which is unknown, and depends on potentially on particular aspect of the two distributions that are unknown. So the question is a more practical question. Without knowing this threshold, can I automatically sample as little as possible of the target data? So here is a setup that we'll use. It's called semi-supervised transfer. And semi-supervised transfer does the following. I have a lot of labeled data from my source P. I have a lot of unlabeled data from my target Q. And I'm going to try to request as few labels as possible in order to do transfer of the target, as few target labels as possible in order to do transfer. So here is a simple heuristic that you can do using these insights from gamma. Only request labels, so sample in those low confidence regions where the local notion of gamma is large. So you can redefine gamma locally rather than define it globally as I did. You can just define it in terms of balls in a region A. And then in terms of the gamma in those regions, if the gamma in those regions is large, you sample. If it's not large, you don't sample. So I'm just describing quickly the high level of the procedure. Okay? And if using the data from P, I was already confident in the label, also I don't sample. So I only sample in those low confidence regions where gamma is large. Okay, where the local gamma is large. The point also that I have to make here is that I never have to estimate the global gamma in this type of procedure. I'm only looking at gamma very locally. Okay, and the above refines some existing heuristics, some existing procedures of Berlin and Erner. Okay, here is how it does. These are experiments on CFAR, on CFAR 10. And in this experiment here, the target data has 50%, is 50% images of cats and dogs, and the source data has less than 1% images of cats and dogs, okay? And we have 20,000 source and 6,000 unlabeled target, and we want to sample as few unlabeled, we want to label as few targets data as possible. So what we do here is that we have a deep neural net that gives us a feature space. We cut off that feature space and then we put the nearest neighbor on the last layer and use the nearest neighbor to implement the sampling procedure I gave before. All right, so the result is the following. Here is the heuristic I described. And this is the sampling complexity, how much target labels are allowed. And quickly, we reach how well we can do on that particular data set. This is the procedure of Erner, the earlier procedure of Berlin and Erner, and these are a few, this is random target, random sampling, and this is the earlier procedure of Erner. Okay, and so we see here that by just following this intuition about gamma, we can quickly reduce the amount of sampling needed. Okay, more than half it compared to randomly sampling, and that's the most important here. All right, so I'll just give a quick summary and tell you about new directions with Steve Haneke. So again, gamma captures a more optimistic view of transferring between P and Q. So more optimistic view in the sense that unless gamma is large, transfer is not hard, right? And gamma is often small in a lot of the situations where other notions of distance between distributions happen to be large. Unlabeled data, interestingly, can only improve rates up to constant. Here, again, I have to qualify it properly. This does not mean that unlabeled data cannot help. There are situations where unlabeled data helps, but in the worst case, unlabeled data might not help at all. Okay. Adaptive sampling is possible even without knowledge of the global notion of gamma here. Oh, and by the way, we can actually show that that adaptive procedure that I presented before also attains the minimax rate, even while sampling much less than random sampling. It still attains the minimax rate. Okay, so new directions. Here are some new directions. So we want to refine gamma. Even though I'm saying that gamma is more optimistic than previous notions of distances between distributions in capture and transfer, it is still of somewhat pessimistic nature. Mainly because we are looking at these differences between P and Q over the entire space, okay, over the entire support of Q. In fact, now, if you think about how people do machine learning, they sort of fix a family of predictors, and then they will really only try to transfer information within that family of predictors. They train a deep neural net on a particular source data, then they want to use again a neural net on the target data, right? So now, if we are looking only within that family of predictors defines a different geometry of the space. And so that geometry should inform which part of the space we are comparing, which part of the support we are comparing, okay? So, so consider the regions of the support that are most relevant to your family of classifiers. So here is a quick example. Imagine in this, this is a cartoon example. Imagine that my family of classifiers consists of just two classifiers, right? This linear separator and this linear separator, both saying plus on one side, minus on the other side. Then I only care about comparing the distributions where they disagree. I don't need to compare the distribution anywhere else because they have exactly the same error everywhere else, okay? And so we can redefine a notion of gamma that just looks at where classifiers disagree. And that notion is always smaller than the previous notion of gamma that I presented. And what we can show is that, and this will appear at NIPS this year, and what we can show is that this refined notion actually captures performance limits that are specific to each class of each set of classifiers that you choose as a practitioner, right? So it's a classifier-specific limits of transfer captured by this other notion. Here is a message that is quite important to me, which is what started this work was not only trying to understand how much I need to sample, but also trying to understand out of all the heuristics out there that people have been using for transfer, which ones are doing something optimal, which ones are using the sample, the new target sample, which one are using it in an optimal way, okay? So what is the nature of optimal heuristics? Now that we understand the performance limit, which heuristics attain this performance limit? Okay, I hope that question is clear. So, and we want performance limits without estimating gamma, without knowing any. The heuristics need to not estimate gamma, and they need to also not know anything about the underlying distributions, because that's how practice is. We don't know anything about the underlying distributions. So which heuristics are optimal? So here are partial results that we have, which is quite interesting. So here is the simplest and most naive heuristic. I take the source data, I take the target data, I combine it, and I pretend that it's from the same distribution, and I run my favorite classifier, okay? So this agnostic type of procedure can be shown to be minimax optimal in various regimes. First, it can be shown to be minimax optimal whenever classification on the target is very hard, so in non-parametric regimes. It also can be shown to be minimax optimal when classification is extremely easy, so in cases where we have absolutely no noise in the classification. Then just doing this simple thing, combining the two data, pretending that it's the same, is minimax optimal, which was quite surprising to us because people have come up with all sort of very elaborate heuristics for transfer. Now, the regimes in between, very hard and very easy, are the ones that we sort of want to care the most about because they are probably the most common. In those regimes, we do not know whether this is still optimal, right? However, here is the form of the optimal heuristics here. I'll describe it, then you will see that it's actually very natural also. So you minimize your empirical risk under the target Q, subject to your empirical risk under the source P being not too far from the best possible empirical risk you could have gotten on the source. Okay, and this not too far, I'm not showing how what this is, but it is a quantity that you can learn from sample. It's just a notion of variance of your estimator that you can learn from sample. So as long as you are within a ball of the best under the source, and you minimize the target under it, this is an optimal heuristics, and it is optimal under any of the classification regimes that we've considered. And that to us was very interesting because this heuristic is very natural. It just says minimize the target subject to the source, subject to not doing too bad under the source. Okay. Now, this is hard to implement in practice because these R hats are classification errors, are classification risks, and they are not easy to optimize. And so one of the open questions here is, can we actually implement this heuristic exactly? And if we implement it, maybe we use surrogate losses to implement it, so convex surrogate losses to implement it. What do we lose? It's unclear to us so far what is lost if we try to implement it that way. Another high-level question is, okay, that one I'll get to later. I have the feeling that this type of heuristic is very similar to what Bayesians will do in practice also. Right, but I can get to it a bit later. What Bayesians might do in practice is use a Bayesian approach on the source, then you get a posterior, and then use that posterior as your prior for the target. And we believe that this might be somewhat related. It remains a bit unclear, but that would be quite nice because this is something that people already sort of do. All right, so somehow we are still scratching the surface of what's possible on the transfer, of the limits of transfer, getting the right notion of distance between distributions, getting a sense of what the right procedures are for transfer. And I've mostly talked about covariance shift, and the result that I showed actually extend beyond covariance shift, where I don't assume that the conditionals are the same. And the extension is actually immediate, although it can be refined. Here, there are questions such as more complex transfer regimes. And by more complex transfer regimes, this is what I'm looking into. The main assumption that has been used by most theoreticians so far is that the Y labels, the classes are the same under the source and the target. Practitioners are attacking problems where the classes are not the same at all, right? And so how do we capture that even? What notion of information is there when the classes are not even the same? So the distributions don't even have, the conditional distributions don't have the same support. What can you say, right? Transfer is related to many other problems in machine learning, multitask learning, where you have not just one source, but multiple sources, curriculum learning, lifelong learning, where you keep the distributions keeps changing over time, fairness, robustness, all these things I believe inherently have a transfer problem at the root of them. And so I'm hoping that this is just a step towards all these other things. So, all right, thank you.